In this lecture, I'll talk about some of the more generic principles of object-oriented design. We've seen a couple of design patterns now. In this lecture, I'd like to give a few examples of how you can apply these patterns. We've seen the grass principles from Larman's book. However, there are a few more generic principles related to object-oriented design that I'd like to discuss now. First, let's talk about how you should apply design patterns. You can try to work top-down. Think about the concepts first and which design patterns are appropriate for the relations between those concepts. You can also work bottom-up. Which pieces does the design consist of? Classes, methods, etc. And once you establish that, you can refactor everything to include design patterns. Christopher Alexander is a well-known architect with a focus on human-centered design. He observes that design is often viewed as a synthesis process, putting parts together to form a whole. You first design the parts, and then the whole comes after that. However, he suggests that this bottom-up approach is not the way to go. When you design a house, you don't think about the types of bricks you need. You first think about the overall design. What rooms, how are they connected? The actual parts come later. When you design software, start with the big picture. You will already be able to identify patterns at this level. Then, start filling in the details. You will again identify patterns and start filling in more details, and so on. By applying design patterns until you end up with the final implementation, you make sure each level of your design adheres to sound design principles. If you don't start thinking at the level of classes immediately, but first at the level of concepts, problems and patterns, this is akin to thinking about the rooms in a house before thinking about the types of bricks. You work from a higher level to lower levels and iteratively refine the design. This also fits well with the idea of first establishing a domain model and requirements, all of which are defined on a high level. Let's look at an actual example, CAD/CAM software. Suppose we want to create software that analyzes a piece of sheet metal containing features. We want to see what to make from the sheet and generate a set of instructions for manufacturing equipment. There is already an expert system in place that can determine how to make complex parts from features. Unfortunately, the software that the expert system needs to use for describing the features is changing all the time. So how do we handle this? Globally speaking, the expert system will use some kind of model of a feature, and there are different versions of that feature model, and possibly more versions will come in the future. So, how to actually implement this? You could create a generic feature class, subclasses for each specific feature, and then again subclasses for each version of that specific feature. You would then get something like this. There are some disadvantages to this solution. Some features will be very much alike, so you will probably end up copying a lot of code. There's tight coupling, because there is a complicated structure of types that the different versions interact with. Cohesion is weak, because functionality is split over many classes. Also, versions of features are not linked. So this design allows you to mix V1 and V2 features in the same model. If a new version of the CAD/CAM software is released, you need to add an extra class for each feature in the system, and this is a lot of work. So let's apply what we know about design patterns to come up with a better solution. So what's the situation? We have different kinds of features: slots, cutouts, holes, and so on. Each version of the CAD/CAM software implements these features differently. A good design pattern to apply here might be the bridge, since the goal of that pattern is to decouple abstractions from their implementations. If you apply the bridge, you get a class diagram that looks like this. There's still a feature class with subclasses for each feature, but now there is an implementation class, which contains each of the versions of the CAD/CAM software. Now the challenge is to determine what methods the implementation class should support. To determine these methods, you need to look at what varies in the versions of the CAD/CAM software and encapsulate those. It should probably have a few generic data retrieval methods to obtain information about each feature, such as X and Y position, length, width, and so on. Now we have determined what the design should look like on the highest level. Let's zoom in. We have a separate class for each version of the CAD/CAM software. So how do we design the part of the software that hooks the CAD/CAM system into each of these versions? In particular, the first version has a complicated interface that doesn't fit well. So what do? Well, we can use another design pattern, the facade, which helps us hide the complexity of this version 1 CAD/CAM software. The second version of CAD/CAM software was less complex, but it doesn't use the same interface as the first version. So, how do we solve this? Here we can use the adapter pattern to provide a translation between the CAD/CAM software and the feature implementation class in our system. So overall, we started with a high-level design that relies on the bridge. When we zoom in, more design patterns, such as the facade and the adapter, are needed to fill in the details. We iteratively refined this design until we are ready to implement it. We designed the system not by thinking in classes, but by thinking in patterns. We thought about the rooms first, before we decided on the types of bricks to use. The same point is made in the book by Shalloway and Trott, Design in Terms of Patterns. Analyze a problem and determine which patterns are suitable. Then apply the pattern and repeat. In principle, this is a good idea, but the solution you find in this way will rely heavily on the list of patterns that you have available. Perhaps there are cases where there is no suitable pattern. Most patterns are quite concrete solutions to particular types of concepts and relations. For the overall software architecture, for example, there is no pattern that you can just apply. In chapter 14 of Design Patterns Explained, you can read more about the theory behind design patterns and object-oriented design. A few important ideas discussed there are the open-closed principle, the LISKOV substitution principle, encapsulating variations, dependency inversion, and more. So next to a good overview, this is also a good entry point for the other design patterns we'll see in this course. The open-closed principle is defined by Bertrand Meyer as software should be open for extension, but closed for modification. What does this mean? You can see this effect take place in many of the design patterns we discussed until now. For example, the strategy pattern can be extended with new strategies, but if you want to modify the interface of how to use these strategies, you need to rewrite the code. The idea behind this is not that modifying your code should be difficult. The idea is that modification shouldn't be necessary. You should design software in such a way that adaptations of that software in the future can be done by extending the software, not rewriting it. Let's look at another principle, dependency inversion. If you look at the bridge pattern, where do you start with designing it? Do you first look at the different implementations, or do you look at the abstractions first? In other words, do you start on the left or on the right? The dependency principle suggests starting on the side of the abstractions, the left side. In the slides of the bridge pattern, we had an example of a game with Mario and Luigi that used different graphics engines for iOS and Android. If you're designing a game, it's much more important to think about the characters in the game and how they behave, than how to implement the abstraction for each, or the implementation for each of the graphic platforms. How you design the characters in the game should not be dependent on details of the graphics engine. In other words, the high-level modules should not depend on low-level modules in terms of design. Also, the implementations are more likely to change than the abstract concepts. Perhaps a new version of iOS comes out, which leads to a new version of the graphics engine. But your Mario and Luigi game design shouldn't have to change because of that. Another example of dependency inversion can be seen here. Big supermarkets deal with invoices for various smaller suppliers. It then also makes sense that the supermarket is the one providing a single format for their invoices. It makes their lives much easier, and for the small suppliers it won't matter much. Dependency inversion is similar to program to an interface, not an implementation. But it also says something about your design starting point, which is on the side of the abstractions. The LISKOV substitution principle, formulated by Barbara Liskov, states that a subclass should support all the behaviors of the base class. This seems rather basic, but remember that when we talked about design by contracts, there were some extra guidelines of how to deal with changing pre- and post-conditions for classes and subclasses. The LISKOV principle covers this as well. Let's see what happens if I break this principle. Suppose we have two classes, square and rectangle. You could say square is a subclass of rectangle, because a square is a special kind of rectangle, one with equal length side. Suppose rectangle has a way to set its width and height. What should a square do? If I change one, I also need to change the other one. Otherwise, the square is no longer a square. So every change in width also changes the height, and vice versa. This enforces the variation that width and height are the same for squares. But now, if you write a unit test for rectangles, that will break when you use it for squares. Even if intuitively a square is a special case of a rectangle, you also have to look at it from a behavioral point of view, taking into consideration the methods that a class has, the conditions, and the invariants. When you look at it this way, from an object-oriented principle, a square is not a rectangle. There's never a single best design that solves all the problems. You always have to balance design principles by closely looking at the problem and estimating what is likely to change, what solution is easier to maintain, and which has strong cohesion and loose coupling. Evaluate your design by imagining it being actually used in a couple of different scenarios. When will your design break? How does it compare to another option? What changes can we easily accommodate? And which one are harder to take into account? The most common design patterns have a recognizable style that use inherent sparingly. The reason is that the patterns follow object-oriented design principles. Larman defines grasp principles. The solid object-oriented design principles overlap with those, but they are a bit more generic, and as such they're also applicable to software architecture. Every class or subsystem should be responsible for one thing. Software should be open for extension and closed for modification. A subclass should support all the behavior of its superclass. Program to an interface, not an implementation. And finally, start with the abstractions, not the implementations. You will never create the best design. Design patterns do not specify an upper bound on software complexity. You can go overboard with them, leading to very complicated code to solve a relatively simple problem. Balance the application of design patterns with what is likely to change in the future versus how much time it costs to implement a pattern. Make sure you understand the problem domain to avoid applying the wrong patterns. Don't try to implement your favorite pattern everywhere just because. Always check whether it makes sense in the context. In short, always question your assumptions. We've reached the end of this clip about object-oriented principles. Please post any questions you have in the Teams channel. Thanks for watching, and catch you in the next one.